How many characters am I holding up? By determining... My name is Ben Yang, and this is Quick. How many characters am I holding up? By determining the length of a string is more complicated than you think. So, how many of you here have ever been in one of those dreaded programming language interview questions, and they ask you a question like, how do you reverse a string? Well, I'm hoping that by the end of this talk, I'll have given you a good answer for that question. So when you take a question like, how do you reverse a string? Or a question like, how long is a string? They're ultimately reliant on the question, what is a character? So what is a character? Is it a byte? Is it a set number of bytes? Is it a Unicode code point? Or is it something else entirely? Well, let's try to figure this out over the next couple of minutes. Let's start easy. Let's start with the English word snail, a string that's just the English word snail. First of all, let's see, what's the length of this? Well, I think that any reader of the English language would probably tell you, yeah, that's 5 characters long. S-N-A-I-L. And the reverse of it should be L-I-A-N-S. So let's see if we can make an algorithm that'll figure this out properly. Let's start with a real simple idea that a character just consists of 8 bits, an 8-bit byte. So we'll start with an ASCII encoded string, snail, and if we break it into chunks of 8-bit bytes, then we get a length of 5. Okay, so this is working, right? So we have an idea that a character consists of 8-bit bytes. And the reverse? Oh, that works too. L-I-A-N-S. Looks good. Okay. So how is this actually being broken up? Well, it's like this. So these are the bytes that correspond to each character in ASCII. And so if we break it up into 8-bit bytes, 5 characters, reverses properly. But this is not the ASCII conference. This, of course, is the Unicode conference. So let's try something a little bit more interesting. Let's try it with UTF-8. Well, even when our string is encoded in UTF-8, it seems to be working properly. Right number of characters, reversing properly. And actually, if you look at the representation in UTF-8 of this string, it looks exactly the same as the ASCII string. That's because, of course, any of the first 128 characters of ASCII is identical to the first 128 characters of UTF-8. Well, let's try something a little bit more interesting. I mean, this is the Internationalization Unicode conference, so let's try to get a little bit more international than just an English language word. Let's take the word shoes. Shoes is the Venetian word for snail. So, any Venetian will tell you that shoes is 5 characters long. S-C-I-U with a grave accent, S. And the reverse of it would be S-U with a grave accent, I-C-S. So let's see how well our algorithm works on this. We'll take shoes encoded in UTF-8, break it up. Uh-oh. Okay, we've stumbled across our first problem. So if we break this into 8-bit bytes, then that's actually 6 of them. And that should be 5, right? This is a 5-character word. And if we reverse it, oh, it actually comes to an error. So we've got some problems here. So how is this actually encoded in UTF-8? Now I imagine you can see your problem. So while the S, the C, the I, and the S are encoded with a single 8-bit byte, the U with the grave accent is actually 2 8-bit bytes. This is because in UTF-8, a single code point can be encoded from anywhere from 1 byte all the way up to 4. And since we don't necessarily know what the content of a string is before we're checking its length, we can't use this as our method of determining a string length or breaking up a string into characters. So when we get into a problem like this, the first answer, of course, is, well, why don't we just try JavaScript? JavaScript can fix everything, right? Well, in JavaScript, strings are stored as UTF-16 encoded strings. And in order to break up a string, it breaks them into 16-bit units, so 2 bytes. Now, does this handle shoes? Yes, it does. If we take the UTF-16 encoded string and break it up into 16-bit units, then yes, we get 5 characters. And the reverse works great too. S, U with the grave accent, I, C, S. And how is this represented in UTF-16? Well, there it is. It's simply every single character is represented with 16 bits, and therefore, if you just break up the string into 16-bit units, then you get your correct count. But let's try something a little bit more interesting. Okay, this looks a little scary, but don't worry, it's just Aramaic. So, in Aramaic, the word for snail is halzuna. And any Aramaic speaker would look at this and say, yep, that is 6 characters long. And the reverse would look as you see there. It would be pronounced something like anuzla. Anuzla. And let's try our UTF-16 algorithm. Here we go. Uh-oh. Uh-oh. So we got a problem again here. Our UTF-16 algorithm breaks it up into 12 characters. Now, why would that happen? It's clearly 6, right? So something's going on here. And if we try to reverse it, oh, it fails. So let's break it up into its 16-bit units and see what we got. Ah, here's our problem. So every single one of these Aramaic characters is represented not by a 16-bit unit, but by 2 16-bit units. This is how UTF-16 deals with any characters that are in the SMP, or anything above the BMP. Now, any character whose code point is above FFFF is going to end up in the SMP. So this poses a problem. It means that if we have any characters in our strings that are outside of the BMP, then they're going to be counted incorrectly by these algorithms. In fact, if you try to do this with JavaScript, you'll actually discover this exact same problem. So you might be saying, well, you know what? I don't really care about Aramaic. I don't care about historical languages or minority languages. Well, first of all, shame on you, because you should care about those things. They're important. But even if you're taking that attitude, I can tell you one thing that your users are almost certainly going to care about. Emoji. So, let's try this string. I heart snail, snail, snail. Well, if you ask me, that looks like 5 characters, length of 5, and the reverse should be snail, 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 heart, I. It's a mutual relationship. So let's see how our UTF-16 algorithm breaks this guy up. Uh-oh. Oh, that's not good at all. Okay, so it actually says, or it thinks that there are 9 characters in this string. Now, that is obviously not right. There's 5 here. And if we try to reverse it, yep, we get an error. And let's take a look at how this is broken up into 16-bit units, and this should tell us what our problem is. Yep, there it is. So notice that the I, being a BMP character, is represented by a single 16-bit unit, but all of the emojis, being SMP characters, are represented by 2 16-bit units. So our algorithm can't distinguish between a character that's below the BMP and above the BMP, and just breaks it up into 16-bit units and gets the incorrect number of characters. So you might be thinking, okay, well, fine, this is Unicode, we're using Unicode, why don't we just break it up into code points? Well, let's give that a try. Let's start with our word snail. Yep, length 5, reverse, yep, looks correct, and here's all your code points. Okay, we're working with something here. Our Venetian word, shoes, length of 5, reverse looks correct. Those are the code points. Yeah, everything's working fine. Now, let's try some of our SMP characters. Yep, halzuna, 6 characters long. Reverse looks good. Yep, and there's our code points. Okay, well, and finally, let's try our emoji string. I heart snail, 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 5 characters, looks good. And the reverse, snail, 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 heart, I, yep, looks great. And it breaks up exactly as you'd expect. Okay, you might be thinking, oh, we're done here, right? And a lot of people may think that this is how you count the length of the string, is by code points. But again, let's try something a little bit more interesting. Let's try this word. It's pronounced ball, and it is the Ewe word for snail. So Ewe is a language that's spoken by about 5 million people in between Ghana and Togo. And the length of this string to any Ewe speaker would be 5 characters long, a, ba, ol. And the reverse would be ball, ba. That's pretty clear, I think. I think that anyone looking at this word would probably say the same thing, even if they weren't an Ewe speaker. So let's try our code point algorithm for determining the length of a string. Here we go. What? 7 characters? Well, that's a bit bizarre, isn't it? And the reverse? Oh, wow, it really mangled it. It actually, something came out of it, which is interesting, but it really mangled it. So we've got one of our accents appears to be now accenting the quote mark. Another one ends up on a B. This is a mess. This is a nightmare. Okay, so let's see what it looks like underlyingly. It's code points, and maybe we can figure out and diagnose what's going on here. Aha, here's our problem. So whereas the A with the accent is its own code point, it's a single code point, a precomposed character, the all and with the accent characters are not. They consist of 2 characters, the all, the base character, the all, and the accent mark itself. So let's try an emoji. Okay, so this is a pretty clear emoji, right? This is a single emoji consisting of this happy couple. And if I look at this, I'm going to say, yeah, that's one emoji, right? Character length of 1. Reverse should be the same because it's just it's 1 character long. And let's try our code point algorithm. 7. So this single emoji consists of 7 code points. Well, what happens when we reverse it? Oh no. Oh, that's not good at all. It seems to have exploded the emoji into 5 different emojis. Actually, I'm not sure that all of those are even emojis. Some of them just look like squares. What's going on here? Well, here's your problem. So the thing is, emojis can actually consist of more than 1 code point. In fact, many do. In this case, this consists of the woman emoji, a skin tone modifier for that woman, a zwidge, that's a 0 with joiner, 2 hands, another zwidge, a man emoji, and then his skin tone modifier. So these all combine together in your font to create a single emoji. Let's try another string. Pakistan hearts snails. This is a nice string here. Look at this. Okay. So how long is this string? I would say it's 3 characters. Pakistan, Pakistani flag, a heart, and a snail. And the reverse of it should be snails, heart, Pakistan. It is a mutual relationship. Well, let's see what happens when we try our code point algorithm. 4. Okay, now it's getting weird, right? I mean, I see 3 characters, but it's saying it's 4 code points. Where do you suppose that extra code point is coming from? And the reverse? Oh no, that's really bad, right? So it apparently, in one way, it's Pakistan heart snails, but when you reverse it, it becomes snails heart North Korea. What's going on here? Well, there's a problem. So what happens is that Pakistani flag consists of 2 code points. So all the flag emojis consist of these two code points. Sorry, all the country flag emoji consists of 2 code points. In this case, there's a P and a K, a special P and a special K that combine to make a Pakistani flag. Now, when you reverse it, it becomes snail, heart, KP. And then KP is actually the abbreviation for North Korea, which is why it produces a North Korean flag. So clearly, our code point algorithm is not working for determining the length of a string. So here's how we answer that problem. There is something called the extended Grapheme Cluster algorithm. It's defined in UAX number 29. That's the Unicode text segmentation document. And what it attempts to do is identify user-perceived characters. It's what we've been referring to as characters this entire time. So what it does is it tries to identify base characters and then mark characters that apply to them and say that consists of a single cluster. And good news is this algorithm is implemented for most of your favorite programming languages. So if you're using Python, there's the Grapheme module that's on PyPy. If you're using Rust, you can use the Unicode segmentation crate. Go has Uniseg. C, C++, and Java, you can use ICU. And there's a couple other libraries that'll do this as well. JavaScript, there are some libraries that will do the Grapheme cluster segmentation. However, some of them appear to be out of date. It does appear that some developers are working on adding it to the standard library of JavaScript. So that could be useful once that comes out. Otherwise, just make sure to investigate fully to make sure that whatever you're using is up to date. And in Swift, actually, you're very lucky because it is not only is it part of the standard library, it's actually the default way of segmenting strings. So in Swift, if you break up a string, it breaks it up by Grapheme clusters. In Python, for example, it breaks it up by code points. In JavaScript, it breaks it up by 16-bit units. But in Swift, by default, it breaks it up by Grapheme clusters. So let's see what this looks like in action. We'll start with our Pakistan heart snails. According to the Grapheme cluster length, 3, all right. And the reverse, snails heart Pakistan, all right, because it breaks it up into these 3 Grapheme clusters. The algorithm doesn't care that the Pakistani flag consists of 2 code points. It collapses them into a single cluster. And our happy couple emoji, yep, 1. The reverse is also 1. This is great. Single Grapheme cluster. And our Ebe word, above all, 5 characters, perfect. And the reverse, all ba, looks great. That's how it breaks it up. Again, the algorithm collapses the all and its accent mark into a single cluster, which corresponds to a visual character. And our I heart snails, 5 characters long, reverses correctly. How about our Aramaic word? Halzuna, 6 characters long, reverses correctly. Looks great. All right, this is how it breaks up. Eagle-eyed viewers may notice actually that Aramaic is indeed a right to left script. And our Venetian word, shoes, yep, still works great, still looks good. And snail in English also looks great. Yep. All right, so it's worked on all the strings that we presented so far. Yay, we did it. We found the algorithm that breaks the string up into characters. And it's worked so far on all of the strings that we've proposed so far. Well, actually, not so fast. Things actually get a little more complicated than this, as you may imagine. Let's take the word melchouet. That's the Breton word for snail. Breton is a language spoken in the northwest of France. So how many characters is this word? Well, to an English speaker, you might say, yeah, that's 9 characters, right? M-E-L-C'-H-W-E-D. But to a Breton speaker, this is actually 7 characters. So how is it 7? Well, let's look at the reverse. This may help. D-E-W-C'-H-L-E-M. Well, you probably figured out by now what's going on. But here's a final hint just in case.
A re PC crabash vel ba huer mer guer wa huer marcalor a huer man a huer.
Yep, that's right. In Breton, C''H is its own letter. So if you ask a Breton speaker, they will say that this is part of our alphabet. If things are collated, then it'll be considered its own letter. And if you ask a Breton speaker how long is a string, they will oftentimes count it as a single letter. So let's try our Grapheme cluster algorithm to see if it handles it. Nope, it thinks it's 9 characters long, and it thinks the reverse is this. Now, that's clearly not right, especially if you consider C''H to be its own letter. Here's the clusters for your information. See, the thing is, the Grapheme cluster algorithm has no idea how to interpret C''H as its own letter because it doesn't know the string is in Breton. If this was an English word, those should be considered 3 characters. Let's try something else. This is a little bit more complicated. This is the Sanskrit word for snail, pronounced shambuka. in Sanskrit, or any Sanskrit speaker would say that this consists of 3 characters, or rather 3 aksaras. The first one is sha, as you can see here. The second is mbu, here. And the third is ka, here. If you were to reverse the 3 aksaras, or 3 characters, you'd get ka, mbu, sha. In other words, kombucha. So this is the traditional way of analyzing a word in Sanskrit, or many other Indian languages as well. Let's see how well our Grapheme Cluster algorithm works on this. Here is Shambuka. Uh-oh, here's a problem. It thinks it's 4 characters. And the reverse, I don't know if you can see, but this is not correct. What it has here is ka, bu, msha. That's not correct. The reverse should be ka, bu, sha, not ka, bu, msha. So let's see how the Grapheme Cluster algorithm broke up this word. Okay, here's the 4 clusters. Let me go over them and show you what's going on. This is sha, so that's correct. And this is ka, and that's correct. But here's where our problem is. The m, the ma, which in the word here is actually combined with the ba, and thus creates a single character with a vowel mark right here, is instead split up into 2. The ma is then given this mark, which basically tells it to not have a vowel and combine with the next character. And this one, the ba, has an u that's attached to it. So why is the Grapheme Cluster algorithm doing this? This just seems like a bug. Well, why not just fix the Grapheme Cluster algorithm? Well, let me try to explain what's going on here. Here's our word, Shambuka, as we've been analyzing. And here's also Shambuka. Both of these words would be pronounced exactly the same, Sha-mbu-ka. In this word here, again we have Sha-mbu-ka, whereas in this word we have Sha, and then M, and it receives no vowel because of this mark, and then Ba-u-ka. Sha-mbu-ka. So these are pronounced the same, but more importantly, they're actually encoded the same way in Unicode. Here's a sha, here's a ma, the vowel killer, the ba, the u, and the ka. But importantly, in some fonts, all of this will render as this, whereas in other fonts, all of this will instead render as this. And for a Sanskrit speaker, or a speaker of many Indian languages, this word will be analyzed as having 3 separate characters, or aksaras, sha, mbu, ka. This word as 4, sha, ma with a mark, ba with a mark, and ka. So importantly here, the number of characters that are contained in a string is dependent on how the font is rendering that string. And the Grapheme Cluster algorithm cannot determine what font the string is going to be rendered in. So it falls back to doing its best to break the string into clusters, and in this case it would do so as sha, m, bu, ka, 4 clusters. Ultimately this gets to the question, what is a character? And the answer is, it depends. It can depend on the script, it can depend on the locale, it can even depend on the font. So if you're trying to answer the question, what is a character, or how do I break up a string into characters, or how do I count characters in a string, or even how do I reverse a string, if you want to get the absolutely correct answer, you need to know what language is the string in, how is the string being rendered, maybe even who's looking at the string. But if you don't have all that information, and you absolutely need a locale independent way of counting the characters or breaking up the string, first of all, don't use bytes. Absolutely don't use bytes. So we saw the problems with that. With UTF-8 and UTF-16, a string can be broken up into bytes, and you can get a wildly different number of characters in the string if you're counting it that way. In UTF-8, a string can consist of, sorry, a character can consist of 1 byte, 2 bytes, 3, or even 4 bytes. And in UTF-16, a character consists of 2 or 4 bytes. But don't even use code points either. You might be thinking, oh, well, you know, just code points. That's the default that people would go to with you when it comes to a Unicode string. But as we've seen as well, a single character can consist of multiple code points. It's very easy for a character to consist of 2 up to even 7 different code points. So instead, use the Grapheme Cluster algorithm. It's available, and it's extremely useful, and it's standardized, and it's available for most programming languages. It won't give you the perfect results, as we saw with our Breton and our Sanskrit example, but it will give you a better result than the alternative. So at the very beginning of this talk, I said that I would give you the answer to the interview question, how do I reverse a string? Well, if an interviewer ever asks you, how do you reverse a string, the correct response is, if you're asking me this question, then you should just hire me immediately, because it's very clear that you're going to need me. Thank you very much for your time. And I'd like to especially thank Manish, who inspired this talk with his essay, Let's Stop Ascribing Meaning to Code Points. Google that, and I think you'll get a lot out of that essay. So I'd like to open the floor to questions now, and thank you very much.